I would have forgotten. I hope it is recording. Yeah, it is recording. Fine. So all of you can see the recording icon, right? It should be there on the top left hand corner of your screen, okay, or your phone. So, yeah, 1 second, I have to admit somebody else. Right. So, if you once again revisiting the idea of an operator. So, as we know, we have a wave function, which is a mathematical function, generally complex in nature. All right. And that has all the information about the system. Now, when we need specific information, we need to extract it from this mathematical function. So, how do we do it? We do it by using a series of mathematical steps, a combination of mathematical operations, and that we call as an operator. So, depending on the kind of information you want, you will need to operate it with that particular operator. So if you want position information, you will need to use a position operator. If you want momentum information, you need to use a momentum operator. If you want energy information, you need to use the energy operator. The reason why I keep repeating these three is that these are the most common ones that we are going to use. Okay, and remember, the energy operator also has a special name. It's called the Hamiltonian. Now, the point is that, yeah, when we have these operators, apart from knowing what an operator actually does, we have learned that they, in the matrix representation, can be represented as square matrices. Now, further, we will go on and look at certain, more information on operators. And the first information that I've put over here is that you should need to know that there is something called as an identity operator. What does the identity operator do? When it operates upon a wave function, it leaves it unchanged. Okay. So obviously, if you look at this as an eigenvalue equation, you will realize that the identity operator has an eigenvalue of how much? 1. Correct? Yeah. So that is something that, sorry, I think I ended up getting myself a pencil, which is not such an good idea. Yeah. Okay. So you will see over here that the identity operator has an eigenvalue of 1. So remember that. Okay. Next, we learned about the product of two operators. And this is where this whole thing, what we have been trying to do about the properties of the commutators essentially comes in. I think I was supposed to admit somebody. Did that person get admitted? I don't know. Okay, anyway, I don't see the message anymore, so I'll leave it. Okay. So you have the product of two operators, and this is what I was trying to explain to you last time. Why is it that AB is not necessarily the same as BA? That's because you have essentially, just 1 second. Yeah, you have essentially this kind of a situation when I write A, B operating on phi. Now remember, when you're thinking about a combination of two operators, remember operators by themselves, though we keep writing it all the time, okay, it doesn't make much sense. Operators have to operate on wave functions. So always think of it as operating on a wave function. You need not explicitly write it, but it should be there in your head. So when I write AB, actually I mean AB operating on a wave function phi. And what does that mean? It means that this particular operator B, which is closest to the wave function, that you will do first, which means that you will do B operating on phi. Once you have done that, obviously B operating on phi will produce a new mathematical function or a new wave function. Okay, unless it's an eigenvalue equation. So once you have that wave function, on that you are operating A. Okay, and that is completely different from the situation here where I'm writing BA operating on phi. Here, what are you doing? You're taking that mathematical function and first operating A on it. Okay, whatever that resulting wave function is, you're operating B on it. So that's why AB need not necessarily be BA. And this should also tell you why the order in which the operators appear is sacred. Whatever appears most close to the right hand side is essentially the first operation which is being done. What is appearing more towards the left will appear later and later. Okay. Yeah. So now just let's have a look at these operators. So remember two things. Firstly is the notation. Okay. I have told you, very, very important. Do not forget the comma. I think most of you are sticking to that. But there are some people who are writing the comma. Of course, I know you have sent it to me in a scanned copy. My eyes are not so great. Okay. So sometimes you may write a comma and it looks like a dot to me. But please, 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 whether you put your commas in your normal writing, okay, properly or not, here please make sure it looks like a comma, even to person with bad eyesight like me. Okay. Yeah. So please make sure that this comma is clearly seen. If you write it as a dot, it looks like a dot product, okay, a multiplication, all right, which is not the same as this. Okay, here the comma has a very special meaning, and as I told you, without that comma, it loses this meaning of being AB minus BA. Secondly, is that please remember square brackets for commutator. Do not make them flower brackets, round brackets. No, they have to be square brackets. But this, I think, I need not tell you. At least the people who have sent me the assignment, okay, have done it correctly. There are whole bunches of people who haven't sent me the assignment. I'm wondering why. Okay. Please take out time and do it, because it will clarify the concepts in your head yourself, and do them yourself, please. Okay. Even if you discuss it with somebody, finally do it yourself. All right. Now, I think relation 1, there was no problem. Relation 2, I actually need to talk a little bit about. Okay. So the first one, I'm going to leave it. I think I had also solved it in class. I've put it up in the solutions, and most people who have sent it to me have done it correctly. So I'm going to this second relation, okay, and I'm going to just talk about the common mistakes I saw, right? So I'm going to stop the share, and I'm going to share screen again, all right? And this time I'll do it with my iScribe. Okay, so is this visible to everybody? Can everybody see the blank page?
Yes, ma'am.
Okay, good. So now listen. So basically, what was this property? It said that commutator of A comma B plus C is equal to commutator of AB plus commutator of AC, right? This is what this is the property you're supposed to prove. Now, very, very important, keep it clear in your head, what are you trying to prove? Either you need to start with the relation on the left hand side, right? Left hand side, or which we write it as LHS. Why do you say left hand side? Because it's on the left, right? Simple. Or you need to start with the relation on the right hand side. Okay. That is your RHS, of course. All right. So you need to start with the LHS and mathematically make it equal to the RHS. You need to be able to show it. Or you need to start from the RHS and go to the LHS. So decide first in your head which one you're going to take. You can do it either way. No problems. So here, for instance, we are starting with the left hand side. Okay. So I will say LHS. Okay. Please don't write equal to and start writing it, because you are trying to prove this relation. This relation has been given to you. You're trying to prove it. So you need to start with either LHS or RHS. Whichever one you're starting, please write it down. So your LHS is equal to, over here, A comma B plus C. Okay. Now, this is the commutator. So this is the second step itself. A lot of people have gone wrong. What should be the correct answer here? The correct next step, it should be A into B plus C minus B plus C into A. Over here, a lot of people have written this correctly, A into B plus C But here in the second step, they have written it as B into C plus A. And I don't understand why. And I'll tell you why it is wrong. Okay. So please bear with me, all those people who did it right, because there was a whole bunch of people who did it exactly how I wrote it here. They wrote it like this. Okay. Which is completely wrong. All right. And I will tell you why. So suppose you're not happy with the second statement directly. Okay. Let us do one thing. Let us write it B plus C as a new operator equal to D. Kindly don't write it as B plus C equal to B, because mathematically that makes no sense, right? B plus C equal to B makes C equal to a null operation, right? A zero. Don't do that. Put some new operator. So now operator of A, B plus C is going to be nothing but operator, commutator, sorry, and not operator. A commutator of A, B plus C is going to be nothing but commutator of A, D. Now write it down. So this is going to be AD minus DA, correct? So this is going to be, now replace your D. What is your D? Nothing but B plus C. And here you will get B plus C A, correct? So which is this step. I hope it's clear to everybody. Now look at the mistake that you will make in that case, okay? So now my LHS, I'm getting the first thing I'm working out here. I will get AB plus AC, correct? Second one here, I will get minus, both of them will be minus, BA minus CA, correct? Yeah. If I had done it like this, what will I get? I will get AB plus AC minus BC minus BA. Look at this term here, this BC operation. Is it there at all over here? No, right? Where did that BC come from? Okay. So please be careful, all right? A lot of people have said that the reason they have done it like this is because of this thing of this cyclic behavior which I told you. This I told you only as a mnemonic, as a way to remember how to write the terms in the fourth relation, okay? Not here. All right, it is only a mnemonic, please. And I will explain it a little more in detail. But here, please remember, just put, if you have a combination of operators, put it as a new operator. Put it as D, Q, R, anything you feel like. Write it down in terms of those two operators and then expand that D, Q, R, whatever you have written. Okay. Just like I put it as D over here and then I wrote the D as B plus C, do that. Okay. Take some few extra steps. Okay. But this is not correct. What you did over here is not correct. All right. So this, please remember, this was a common mistake I saw in problem 2. In case you haven't understood so far, because I've tried to write to each one of you as to what has gone wrong, and I've asked you to look into the solutions. In case you still didn't understand, this is the reason why I'm telling you that you went wrong. Okay. I hope it is clear now. Right. So now I'm going to stop sharing this and we will have a look at the third problem and see what all mistakes happened, okay, over there. All right. So the third one was this, right? Yeah. Which if you remember, I actually did in class. But nonetheless, somehow, again, there were issues when people try to solve it. I'm very happy when I saw those issues. I'll tell you why. Not because I'm happy you went wrong, but it also showed me that you weren't blindly copying what I did in class or blindly copying the solutions and giving it back to me. And that actually means a lot. It means that you were trying on your own, and please keep it up. Okay. I'm very happy about that. Okay. Because I realized that you were actually trying to do it on your own and nothing like it. Okay. Please think on your own. Try to do things on your own. That's the only way you will learn. All right. So let me just tell you what were the problems I saw with the third one. Okay. I'm just taking a little more time over here. It is all right as long as you people learn. All right. So let me just again share my iScribe with you. Okay. Okay. So we are back here and let's have a look at the third relation. Okay. So the third relation, what was it? Essentially, it said A commutator BC, okay, correct, is equal to A commutator BC plus BAC. Okay, and to the people who did this wrong, I kept saying order of operators is very, very crucial. It's something you cannot change. Okay, and I will tell you exactly what I meant by that. Now here, suppose you're trying to solve it with the RHS, okay, right hand side. So you write RHS, okay, and then work your way to the LHS. Sometimes, you get confused. So you may do the RHS and end up with the RHS. It's no use. If you are starting with the RHS, your last one should be equal to the LHS. Then you write RHS is equal to LHS, hence proved. Correct? Yeah. But you cannot just end up with RHS equal to RHS. I know that things are equal to themselves, right? 2 is equal to 2. 7 is equal to 7. 13.6 is equal to 13.6. Okay. There's nothing surprising about that. Correct? Yeah. So please remember that what you need to do. There's some people. All right. Yeah. What you need to do is to start from one side, end up with the expression on the other side. Start with RHS, end up with LHS, start with LHS, end up with RHS. Then your proof is complete. All right. So now your RHS, okay. What did we say? We have this term A comma B C plus B commutator of A C. Now let's have a look at this term here, the first term. You are rating A, B, C, which means this is AB minus BA C. Okay. Lot of people have confused it with this. What is this? This is nothing but C AB minus BA. Now remember what I told you earlier. Okay. What I told you is that in this expression, it means you're first operating the wave function with C. Okay. And then you're operating with AB minus BA. In this second one, what are you doing? In the second one, you're first operating with AB minus BA. This is your first. And then you're operating with C. They are not the same. They are not the same. All right. So you cannot mix up the order. So let me just expand this again. I think I'll have to go to another page, but let me try it over here. So you write this as AB, A comma B, C. So this is nothing but AB minus BA, C, which is nothing but A, B, C. I cannot change this order. Minus BAC. If I could change the order, this would always be 0, right? Yeah. Then what do I have over here? I have this one. I have BAC. Oops. I think my refill is getting empty. This will be equal to B, and then I have AC minus CA, which will be BAC minus BCA. Right? Now, please note again, BCA
is not the same as BAC, nor is it the same as ABC, right? But this BAC and this BAC, this one and this one will get cancelled. Now what are you left with? You're left with ABC minus BCA. Please note that here, when you take out anything common, all right, you cannot take out anything common. You will write it as A BC minus BCA, which is going to be nothing but commutator of A, B, C, right? This is what you will do. Somehow I remember another issue with this, but I can't remember what it was. I think it was essentially the taking out of, people tend to write this as basically CAB, which is wrong. Okay, you cannot do it like that, and I hope you've understood why. Right now, let's go to the third one. Sorry, the fourth one. Let me just explain what was the issue with that. Yeah, so the fourth problem, if you remember, okay, was essentially, this is where I talked about having this cyclic thing. Okay, so there we had A comma B plus C plus B comma C plus C commutator A plus C comma A comma B. Okay, this is
Ma'am, it's B comma C, ma'am, in the first term.
sorry.
Yes, ma'am.
Thank you very much.
Yeah, sometimes I just run off with myself. It's looking like a mess, right? 1 second. I think I can erase it. Let me do that. Very sorry about that. It's not erasing. Oh, nice. Okay, I hope you can figure it out. All right. Yeah, so let me go back to my pen. Right. Okay, so now, so I hope you can figure out this is not a plus, this is a comma. All right. So now, why did I say cyclic? Okay, why did I say cyclic? A to B to C to A. Please note here, A comes first. All right, 1 second, I have to admit somebody. A comes first, B comes second, C comes third. Okay, and then I maintain that order. For here, in the second term, B is coming first. Okay, so this is coming first. After that, which should appear? C. After that, which should appear? A. Okay, right? Here, which is appearing first in the third term? It is C. So C is first. So if I do this is first, I still continue in this order, correct? So then A should come next, as you can see, and then B should come third. This is what I meant. Okay. Now in this expression, suppose I had changed this one, I had reversed the cyclic order. So I had written B comma A comma C. Then this relation would not work out. Okay, it wouldn't work out. It would not be equal to 0. This is the important thing. That's why I put cyclic, so that you remember how to write these terms. Okay, how to write these terms. All right, not for any other reason. Is this clear? Now here, people have tried to do it using property, the third property. You can definitely do it like that. So let me just show you. Your A comma B comma C is now what? It is basically A comma, you have now BC minus CB, correct?
This is the commutator, which is going to be using property 2. You can write it as A comma BC minus A comma CB. Correct? Now, this itself using property 3, you can write it as A comma B C plus B A C, right? And this second term will become minus. Here you will have, what is it? A C B minus C A B. Okay. Now please look at it. Here AB is coming first, C is coming second. This last term here, C is coming first, AB is coming second. These two are not equal to each other. All right, so they will not cancel out. Please understand, the first term and the fourth term are not going to cancel out. Similarly, if you look at it here, this second term here, look at it carefully. B comes first, AC comes second. And in this term here, AC comes first, B comes second. It will not cancel out. So the individual terms are not equal to 0. A lot of people have made this mistake. You can expand it out and write it whichever way you do it, it will not come out to be 0. Please remember, if it had come out to be 0, I would have written it as A comma B comma C is equal to 0, right? Why should I would have written it like this, right? Why should I write such a complicated expression here? Yes? So the individual terms don't go to 0. All right? So all of you who haven't done the assignment yet, please do it, because this is going to make less sense to you, right? All the people who have done it, whether they have done it correctly or wrong, are understanding beautifully what I'm saying right now. People who haven't done it are not understanding. And that is your fault. Okay? If others could find the time to do the assignment, I don't see why you can't. Okay? It's not that you're more busy than your other classmates, right? Yeah? So please, those who haven't done it, you will not be understanding right now. Kindly take the effort to do the assignment, and these will make sense to you, and this will help you understand what is going to be taught next. Is this clear? Okay, so the individual terms don't go to 0. Work out all the terms. Okay, work out all the terms. Work out, so this is obviously not correct. Okay, work out what is B comma A commutator of C comma A. Okay, work out this. Then work out this. C comma A comma B. Work out this. Add all the 3 and you will get a 0. Okay, it's only on adding the 3 you will get the 0. Individual terms are not 0. No matter which way you do it, you should get the same answer. Is this clear? And I'm very happy with those people who use property 2 and property 3 to get property 4. Very good. That's the way to go. Okay. You also got the expansion of each of these terms correctly. Excellent. All right. Just one more step. Remember, order is sacred. Okay. You cannot switch orders in operators. All right. You cannot take it for granted. All right. And only then you will get the correct answer. Is this clear? Okay. So this is for those people who have been doing the assignments. Those who haven't done the assignments, if you have listened to me, if you have understood, please go back and attempt those, and I'm sure you will get them correctly. Okay. And I'm very, very happy with all those people who tried to do this, tried to do it on their own. Okay. Yeah. Because that is the only way you will learn. So, my to all those people who did the assignment. And even if you got it wrong, doesn't matter. That is the way to learn. Okay, I'm very happy you tried it, and I hope you will continue like this. Right, so now let me just go back to this. Okay, so I haven't managed to finish the slides properly. Let me just again, yeah.
I will go back to full screen. All right. So let me just go to the next one. So what else did we learn? We learned about inverse of an operator. Okay. And an inverse of an operator, we said that, okay, if there is an operator A and there exists another operator B such that B operation with A makes it equivalent to an identity, then we say B is the inverse of A. Okay. So I was writing out, of course, about the adjoint operator, and I ran out of time for whatever reason. So I will now go back to my iScribe, and we shall continue the rest of the recap. So remember, adjoint of an operator is an extremely important concept. Adjoint of an operator. And why is it an important? So basically, if A is an operator, then adjoint of A is written as A dagger, right? I hope you all remember this. And how do you essentially define this? So essentially, as I told you in the Dirac bracket notation, we could write it like this, correct? Just 1 second. Let me just get back to the types of operators. I should not make mistakes over here. Sometimes I make stupid errors. Yeah, so I made a mistake as usual. So if I write it like this, okay, it will be essentially nothing but a phi. Okay, or if you want to write it, so if you remember, essentially if I have phi a psi, this can be written as a dagger phi psi. Okay, so this is how you can write it. All right. Now, please remember that you learned for Hermitian operators. Hermitian operator, what was our definition? Our definition was that phi a psi is equal to a phi psi, right? And if you compare this and this, you will realize it means that A must be equal to A dagger. All right. So please remember, if A is equal to its adjoint, it is a Hermitian operator. And in the matrix notation, how do you go from A to A adjoint? So A to A adjoint, you will have to do a transpose. What does transpose mean? Transpose means that you change the rows into columns or columns into rows, whichever way you want to look at it. Okay. And you do a conjugation. What do you mean by a conjugation? You replace each and every element by its complex conjugate. So if it is an element is a plus ib, you replace it with a minus ib. Okay, so that is how you do it. So this is an adjoint operation. Apart from this, what else did I tell you? I'm going to now change the page. I will do it here as well as I'll do it over here because I keep forgetting sometimes. Yeah. We learned something called as a unitary operator, right? Please remember, I'm not throwing things at you. I'm telling you things which we will require later. Okay. And what is a unitary operator? A unitary operator, let us say we call it U, is such that your U dagger is equal to U inverse. Okay. So the adjoint is the inverse of the operation. So in other words, U dagger U is equal to U dagger, which is equal to I. Okay. So this is the definition of a unitary operator. And we will find that these are actually very, very important for us. We will see why. Also, we learned about some relations with uh, this thing, dagger. And I will just write them down for you. Okay. So one was, of course, that if you have a scalar operator and you try to take the transpose conjugate, what will you get? You will get C star A dagger. Also, if you try to do it for a sum of two operators, you will get A dagger plus B dagger. And if you try to do it for a product of two, you will get B dagger, A dagger. Okay, so this is what you need to remember. Right. So apart from this, I think, I think we will now go on directly to
Excuse me,
what
ma'am.
is. Yes, please.
Ma'am, you said in a product dagger, it can become A dagger and B dagger, ma'am. Is it wrong with that?
In what
The third,
sense? Let me just write it out. Are you
the
asking the
third
question that this
AB whole. Yes,
is
ma'am.
equal to A dagger, B dagger?
Yeah. Is there any wrong with that?
It's absolutely wrong. Okay. You can never write it like this. And the
Okay.
basic issue is with, think about your matrices.
Hmm.
Okay.
Hmm.
Think about matrices. Try to
Hmm.
take transpose of matrices. Okay.
Hmm.
So if
Hmm.
you have matrix A, matrix B, matrix product of AB transpose will
Hmm.
always be B transpose A transpose. Okay. So it
Hmm.
follows from there. All right.
Okay.
So
Yes,
please
ma'am.
look up your matrix properties. I think you would have done it in your BSc, right?
Yes,
Matrices.
ma'am.
Yeah.
Hmm.
Try to look up the transpose. So this happens when you actually change rows into columns. All right. So
Yes,
the
ma'am.
same formalism follows here. All right.
Hmm.
There
Yes,
is
ma'am.
no choice. This will never ever be correct. Okay. This is never
Okay,
ever
ma'am.
correct. Okay. It's always wrong. Okay. Big wrong. All right. It will not be correct. Hmm?
Okay, ma'am.
Okay, so it may work out in the case of certain special matrices, like if both of them are identity, like A and
Hmm.
B are both equal to the identity, then you can write AB dagger is equal to A dagger B dagger. Okay,
Hmm.
but that is
Yes,
a
ma'am.
very special case. Most cases it will not work out. All right. Okay.
Okay, ma'am.
So be careful there. Yeah.
Yes, ma'am.
All right. So now, what did so we went on to a very special thing last time. We talked about commutation. Okay, so the link between commutation of two operators A and B and simultaneous eigenfunctions. Okay, so now very important, let's just look at the concept of simultaneous eigenfunctions. I kind of moved through this quite fast last time. What do I mean by a simultaneous eigenfunction? So I mean that let me pick up a wave function psi, okay, and I have two operators A and B. If psi is a simultaneous eigenfunction of both A and B, what will I get? I will get A psi equal to some A psi and this B psi equal to some B psi. Okay. Now please remember this number A and this number B are of course not equal. They may not even be the same dimension, right? So for instance, A could be an operator for position. B can be an operator for energy. So A will be a number which will give you position. So it will be in length, correct? B on the other hand will be an eigenvalue for energy. So it will be in dimensions of energy, correct? So remember the A and the B will not be equal. But if this psi is such that it gives you a relation like this and a relation like this, then we will say psi is a simultaneous eigenfunction of A and B. Now, if every eigenfunction of A, okay, so every eigenfunction, which means all the eigenfunctions of A, is also an eigenfunction of B,
then I can make two statements. I'm going to make two statements. One, A and B share a common set of eigenfunctions. Okay, all right. A and B share a common set of eigenfunctions, and there's a special way of saying this. What do you say? You say that A and B are compatible. Okay, so this is a special word you're learning now. And the moment you hear that A and B are compatible, or any two operators are compatible, what you have to understand from that is that they share a common set of eigenfunctions, or every eigenfunction of their psi is such that you can write down this equation, okay, this equation here, and you can also write down this equation here. Okay, so now what we are going to do is we are going to try and find a connection between commuting property and common set of eigenfunctions. Okay, this is what we are going to try and do. All right, so I already showed you one part of the proof last time. I will just repeat it a few steps and then ask you whether you have any doubts, and we will then go on to trying to prove the converse, okay, which will be the more loopy proof. Okay, yeah, it is not going to be as simple as the first proof. Okay, so I need to change pages. I will change pages here, and I've changed pages here. All right, so what was the first one? If you remember, it said that compatible observables. Please remember what observables are. Commute. Now, when I say something commutes, what does it mean? Essentially, that the commutator A, B minus BA must be equal to 0. Correct? Or the commutator AB is equal to 0. Correct? This is what we mean. Right? Now, here we will start off with the first thing, compatible observables. What do we mean? So, let us have two observables A and B. It means that every eigenfunction of A is also an eigenfunction of B. So they have a common set of eigenfunctions. So let their common set of eigenfunctions, I'm going to write it as ui. Okay, we'll write them as ui. What does this mean? That it means that if I do A operating on ui, I'm going to get some ai ui. And if I do B operating on that same ui, I will get a bi ui. Okay, this is what we mean. What are we supposed to prove? To prove that, so I'm setting up what we are going to prove, that commutator of comma B is equal to 0. Okay, or in other words, we have to prove that the operation AB is the same as the operation BA. So I'm trying to prove that. So let us start off now with operating AB on UI. What is this? I have told you before, this is nothing but A operating on B of UI. But this we know is nothing but BI UI. This is just a number, so we can pull it out. It will come to this. Because why? A is a linear operator. Remember the linear operator definition. That allows for this, okay? That allows me to go from this step to this step. Because A is linear. Okay. So now here we go. This is BI. And here AIUI will be nothing but, sorry, A operating on UI will give me AIUI. So this can be now written as BI AI on UI. But BI and AI are just numbers, and we know that numbers commute with each other, correct? So we can write this as AI BI UI, correct? Please remember, this is because why? BI AI is equal to AI BI. The only reason I can do this is because both AI and BI are numbers. Okay, they are not operators, they are numbers. All right. So here now we can write this as AI BI UI, which is equal to AI, and this now I'm going to replace with BUI. Then I can write this as BAI UI. Why? Because B is linear. How do I know A and B are linear, please? I know that they are linear simply because they are observables. If they are observables, they are linear. Okay, please remember this. Okay, you remember all those properties I put for observables? We did that a few classes back. Kindly go back and refer to your notes. Then what happens over here? Now I can then write it as B A U I, which is equal to B A U I. Is this good enough? No, this is not good enough a proof to say I still haven't proved this. Okay, I have to prove this for every psi. I have to prove it for every psi belonging to the vector space. Okay, I have to prove it for every psi belonging to the vector space. Now comes the rescue that A and B are observables. Okay, since A and B are observables, okay, what is the thing? That every psi belonging to the vector space can be written as psi equal to summation over I Ci Ui. Okay, so thereby now AB operating on this psi will be equal to AB operating on summation over Ci Ui, which can be written now. I can put the summation here, I can put Ci, and I can put AB operating on Ui, which is going to be summation over I Ci. But I know from here that AB operating on Ui is the same as BA operating on Ui. So I will write it as BA operating on Ui, which is then going to be equal to BA operating on summation over I Ci Ui, but this is nothing but BA operating on psi. Okay, so I have proved now that for every psi belonging to the vector space, okay, so I'm going to write this in the next page. I'm also going to change it here, don't worry, I remembered. Therefore, for every psi belonging to the vector space, A B acting on psi is equal to B A acting on psi, which implies that AB is equal to BA, which implies that commutator A comma B is equal to 0. Is this clear? Very, very important. That if two observables are compatible, that is, they share a common set of eigenfunctions, then they commute. So remember, we have proved one way that if they have a common set of eigenfunctions, they commute. Now comes the tricky proof, which is that if they commute, they have a common set of eigenfunctions. We have to prove that. Okay. Now, why is it so important? It is important because I've told you that the eigenequations link up with measurements. Okay. And what commutations or lack of commutation essentially tells you whether you can simultaneously measure two quantities or you cannot. Okay, this is what we are trying to do. So let me have a look at the time. I think I took a very long time today. Okay, I've almost run out of time. All right, let me at least set up the problem and then we will move on. So what is the converse? The converse is that if two operators commute, they have a common set of eigenfunctions. Okay, so this is what we are going to try and prove. All right. So how do we go about it? Okay, so the way we go about it is like this. Just 1 second. Just 1 second. So in this, what do we know? We know that AB is equal to BA. Okay. So what do we try to do now? Let us say that, okay, UI is an eigenfunction of A. Okay, let us say that UI is an eigenfunction of A. To prove that UI is also an eigenfunction of B. Correct? So we already know that if we do AUI, we will get AIUI. What we have to find out is what is going to happen when we do BUI. Okay. All right. We need to show that it will be something like a number times UI. Then we have proved it. All right. So let's start off. All right. So we will start off with doing, let us say, A operating on BUI. Let's do this. So this is going to be nothing but AB operating on UI. But we already know that AB is equal to BA. Why? Because we have already said that the two operators are commuting. They commute. Okay. So this is going to be the same as BAUI. Right? Now, this is therefore going to be BAUI, which is nothing but BAIUI. Right? So this will be nothing but AIBUI. Okay? Why do we say this? Because B is linear. Right? which is going to be now, okay, let's have a look at this step itself. This A B ui is equal to ai b ui. Let's look at this. What is this telling you actually? That A operating on this quantity b ui is equal to a number. What is that number? ai times
Eigen
b ui. Any problems, please? Any doubts? Any doubts? I thought I heard somebody say something.
no, ma'am.
Okay, fine, no issues. All right. So what does this actually tell you? Please look at it carefully, this one, and you will realize this is nothing but an eigen equation. It's an eigen equation for A. What is the eigen function here? It is b ui. What is the eigen value here? It is bi. Okay. Sorry, not bi. My mistake. It's ai. Yeah, sorry. Okay. So what we have ended up proving over here is that B operating on ui, that wave function, is also an eigenfunction of A, and it has eigenvalue ai, right? Now we can have two options. One option is that ai is non-degenerate. Okay. The other is ai has a degeneracy of, let us say, n. N will be some positive integer. Okay. So we can have two options, that it is non-degenerate or it has a degeneracy of n. And the way we tackle the two situations is going to be slightly different. So what's the time now? Okay, it's 13:04. I mean, it's 4 minutes past my end time. So please, we will take a break now. Okay, also the refill of my iScribe pen has somehow stopped working. So I need to replace it. All right. So we will meet back in an hour's time at 2 o'clock. You know that, right? I will send you another invite right away. Please charge your phones, have your lunch. So charge both your phones and yourself, and we will meet at 2. Okay. So I will stop right now, and I will start off first by asking you whether you have had any doubts so far. Is that all right?
Yes, ma'am.
Okay, fine. So I will stop the meeting now, and we will meet back at 2. Okay then. Bye.